Electromagnetic radiation, which includes the visible light range, is the only source of information available about distant stars and about the galaxies they form. Therefore, astronomers place their full confidence in the Doppler effect, especially when it comes to assessing the distances at which stars are supposed to be placed. Imagine the extent of the damage if someone could somehow show the world that the Doppler effect would be nothing more than an optical illusion, only related to the memory of who observes. It would be like pulling the rug under many people's feet. Do you think I know how to do it? Of course not. Neither is necessary, since many others already did it. This is the case of Einstein with his work on the photoelectric effect, 1905, showing that electromagnetic radiation is coherent or, in other words, discontinuous. Planck, despite providing the subsidy and the novelty of the energy quantization of the oscillators, continued to treat the radiation as if it were an electromagnetic wave. That is, although he accepted that the light emitted by the source, for example, a star, was discontinuous, Planck believed that it would propagate in the space like an electromagnetic wave. Einstein's hypothesis suggests that light, as it traverses space, behaves not as a wave, but as a particle. Physics 4, Halliday and Resnick, page 281. The physicists and astronomers of our day, mimicking Planck, cling firmly to the postulates of classical wave theory, because they could not admit the hypothesis that they could no longer rely on the Doppler effect as a reliable tool. Just do not see the truth, who does not want. In this article I tried to collect some existing evidence and to elaborate, on my own, some reasonings that are available to all. The first problem with the Doppler effect is that it has been borrowed from the behavior of sound waves. The reasoning is that if sound propagates in the form of waves and so does light, nothing is fairer than to take advantage of the properties of contraction and expansion of sound waves. A sound gets louder when the source comes in and lower when it goes away. In the case of stars, the light tends respectively to blue or red. For me, it is difficult to understand such borrowed resemblance, especially when it is known that light propagates in the vacuum without difficulty, which does not happen with sound. No use shouting in the void, because no one will listen to you. Sound needs matter to move in space, which does not extend to light. Because it is a transverse wave, or that oscillates in planes perpendicular to the direction of propagation, the light allows its polarization. This does not apply to sound waves, which are longitudinal. The quantization of energy brought some subsidies in this field, which could explain some incongruities. The first is that the quantization of light energy, which does not extend to sound waves, would be directly related to the principle of uncertainty. We see that the state of affairs described by the uncertainty principle is a direct result of quantization. Quantization of electromagnetic radiation requires that at least one unit of light, a quantum, be scattered over the particle or, therefore, that no light be scattered. Fundamentals of Modern Physics, Iceberg, page 141. To illustrate the uncertainty principle, Bohr would have quoted, in 1928, the example of a microscopist analyzing a sample. Consider a measure taken to determine the instantaneous location of a particle by using a microscope. In such a measure the particle must be illuminated, for, after all, they are the quantae of light, scattered by the particle, that the microscopist sees. This is one of the characteristics of our memory. Particles can never be directly observed. What we see would be the result of the translation of information made available by the light scattered by the particle, and whose time for its decoding does not exist in practice. That is, the quantum scattered is delivered by nature already, and the quantization of energy is a timeless process. When you cannot measure any interval of time that separates us from a particle, however small it may be, so does the measure of the motion of the particle. That is, there is no motion in the absence of time, which concludes that particles in spacetime need to be in continuous and relative motion, or will cease to exist, because they cannot be remembered. This puts us in direct and continuous contact with our past, apparently reversing the direction of the arrow of time. Although it continues to point in the direction of the future, it is only from our past that we can remember. We conclude that, in this case, the light and cosmic radiation, emitted by the stars, could only be coming from our past. Hence the term cosmic background radiation. Timelessness, inherent in the quantization phase of energy, would justify Einstein's thought that light would use its corpuscle-like appearance to move in a vacuum, not a wave. This is due to the conclusion, already mentioned, that there is no movement in the absence of time, which would be fundamental for the survival of the electromagnetic waves. Similarly, Doppler and its redshifting could be rightly questioned, because it cannot be measured directly before the photon scattering. Doppler could be considered an optical illusion if it had been conceived in the future or within the comet light of any event, gaining meaning only inside space-time, when we have already discovered ourselves by looking continuously at our own past, a dimension of time that no longer exists. Another interesting feature of the quantization of energy would be that, since it would not depend on the existence of a measurable time, the process would equal the energetic extremes of the light spectrum of the galaxies, at least until the photon scattered. This means that the celestial vault would be crystallized to our point of view, being evaluated in the form of isolated snapshots of our own past. In the case of the visible light range, it would not be possible to know, for example, if the ultraviolet would be reaching the front of the infrared or vice versa, since the zero time frame would have permanently fixed in the position of each isolated observer. Because of the existence of measurable time for the quantization phase of energy, we would still have the feeling that light would have been retained in our future, assuming its limited and constant velocity only in the past, when time became measurable. This would shield a direct access to space, since they are the quaternaria of light, scattered by the particles, that allow us to see them in an indirect way. Therefore, we should give greater importance to the behavior of light and its simple harmonic motion, in order to unlink it from space. This attitude would demystify the idea that light and space would form a whole, a single thing. This thought would be behind the misuse of the Doppler effect, aiming at the evaluation of distances and velocities, either distant stars or subatomic particles. It is easy to conclude that if light and space formed a whole, there would be no uncertainty in the position of light sources, as in the case of stars. Our present behavior hurts this principle, for we usually treat the future as if it were an inverse image of our own past. For example, if a laser needs 1.2 seconds to reach the moon, it is logical to conclude that it will take the same time to travel in the opposite direction. This really happens in practice, but it is still dependent on the existence of the isolated observer. This observer, in turn, will continue to depend on the measurability of time, without which his memory would lose its meaning.